machine learning, where classification falls. It falls under supervised machine learning model. And we talked about what is the difference between classification and regression, where classification gives a discrete output of example labels or categories, and regression gives a continuous output where, let's say, for example, a real estate question of like how much does the house cost, you can solve it through regression and not classification. And if the same problem is can be modified into a classification, if you could change your output to either a high cost or low cost classification. That said, let's move on. So as I said, here's a good example. So regression, when you say, okay, what is the temperature going to be tomorrow? It's going to predict a exact number, whereas in classification, it's going to predict if it's going to be cold or hot tomorrow. This is a very nice example. Anyway, let's talk about the types of learners in classification. So based on the model's capacity to learn, we have two types of learners. One is the lazy learner and the other one is the eager learner. So what lazy learner does, it simply stores the training data and wait until a testing data appears. And when it does, classification is conducted based on the most related data in the stored training data set. So compared to eager learners, lazy learners have less training time, but they take more time to make the prediction. And eager learners are classification-based models that train on the given training data before receiving data for classification. So it must be able to commit to a single hypothesis that covers the entire instance space. So due to these style of model construction, eager learners take a long time to train, but less time to make predictions. So here are some examples of types of learners in classification. Lazy learners are KNN and case-based reasoning, and eager learners are decision tree, naive Bayes, and artificial neural networks. So again, they just store the data set without learning from it, and they start classifying the data when you provide the test data. So it takes less time to train, but more time to actually predict. And eager learners, when it receives data, it starts classifying immediately. So it has a lot of time to train, and it takes very less time to make the prediction. All right, now that we have seen what classifiers are, classification algorithms are, let's start with a simple one, the naive Bayes classifier. So this is how classifier for, the Bayes theorem is. So naive Bayes is a probabilistic classifier inspired by the Bayes theorem. And under a simple assumption, which is the attributes are conditionally independent. That is, let's take for an example, a flip of coin, right? So if you are going to flip the coin 3 times, each flip is conditionally independent of each other. See, the classification is conducted by deriving the maximum posterior, which is the maximal P of the condition when X happens, with the above assumption applying to Bayes theorem. So this assumption greatly reduces the computational cost by only counting the class distribution. So even though the assumption is not valid in most cases, for example, it's valid in the flip of a coin, but it might not be valid in real world cases because usually one incident is dependent on the other. But we still go for this assumption because it reduces the computational cost. And surprisingly, naive Bayes has impressive performance in a lot of real world problems. And that is why it is one of the popular classification model available for us. So again, so we're going a little deeper into Bayes' theorem and naive Bayes. So naive Bayes is a very simple algorithm to implement, and it has good results in most of the cases. And it is easily scalable to larger data sets as it takes linear time rather than by expensive iterative approximation, which is common in other types of classifiers. So here we'll talk more. What it does is that it assumes that the effect of the value of the predictor here, X, on a given class C is independent of the values of other predictors called class conditional independence. So what it's saying is the probability of C happening given X is independent of probability of the class C happening itself, which means it says the likelihood of X happening with C multiplied by the probability of the C happening divided by the probability of X, or the predictor variable happening. So this is a very simplified formula of the Bayes theorem, and this is what we use to classify our naive Bayes classifier. So again, a simple explanation of what these values mean. So you can see this is how often C happens given X, and this is how often X happens given C, and this is probability of C happening, and this is probability of X happening. So it's the same as I explained before, just in better words, I guess. Again, some examples of using this algorithm yeah, so this is based on the notebook. So we'll talk about the notebook towards the end. So I'm just going to skip this for now. Alrighty, so types of naive Bayes classifiers. So usually it's used to classify normal distribution, but it can also be used for multinomial and Bernoulli distributions. So in Gaussian naive Bayes, continuous values associated with each feature are assumed to be distributed according to a Gaussian distribution. So again, a Gaussian distribution is also called the normal distribution. So when plotted, it gives a bell-shaped curve, and it's symmetric about the mean. Multinomial naive Bayes, it's a feature vector representing the frequencies with which certain events have been generated by a multinomial distribution. So this is the event model typically used. This type of event model is typically used for document classification. And then we have Bernoulli. In this multivariate Bernoulli event model, features are independent Booleans describing inputs. Like the multinomial model, this model is popular for document classification tasks where binary term occurrences, example, a word occurring in a document or not, or a feature is frequent or not. So it's binary classification is when you go for Bernoulli's naive Bayes classifier. And let's talk quickly on the pros and cons of this model. It is easy and fast to predict. When assumptions of independence holds, a naive Bayes classifier performs better compared to other models like logistic regressions and other models. It performs well in case of categorical inputs. And for numerical inputs, normal distribution is assumed. So if you're trying to solve for a numerical input, you want to make sure that it passes the normality test or for assumption. The cons are if categorical variable has a category, which was not observed in training data set, then this model will assign a 0 probability and will be unable to make predictions. So this is often known as zero frequency. And to solve this, we can use the smoothing technique. One of the simplest smoothing technique is called Laplace estimation. We will not talk about it in elaboration today, but we'll be going over that soon. On the other side, naive Bayes is also known as the bad estimator. So the probability outputs from predictions are not to be taken too seriously. So it is prone to bad estimation. And because the another limitation is the assumption of independent predictions. In real life, it is almost impossible that we get a set of predictors which are completely independent. So these are some of the cons of the model. And here is some application of the model, real-time predictions. So it is an eager learner classifier. So it is fast in giving out predictions. So it can be used in any real-time predictions and multi-class predictions. So we don't have to stick to binary outcomes of either 0 or 1. It can be used for multi-class predictions. And also it is very much popular for text classifications, spam filtering, and sentiment analysis. So naive Bayes classifier, it's mostly used in text classification and also in recommendation systems. All right, next we have to talk about logistic regression. We will go about what the logistic function is and how it is represented. And then we will talk about learning model, the algorithm itself, and the assumptions that goes behind the model. And then we will talk more on the logistic regression itself. So let's start with simple logistic sigmoid functions. So what is this? Logistic regression is named from the function that is used at the core of the method, the logistic function. The logistic function, also called a sigmoid function, was developed by statisticians to describe properties of popular growth in ecology, rising quickly and maxing out at the carrying capacity of the environment. So it's an S-shaped curve that can take any real value numbers and map it to a value between 0 and 1, but never exactly at those limits. So here you can see this is the function that is run behind it, which is 1 divided by 1 plus e to the power of negative value, where e is the base of the natural logarithms and value is the actual numerical value that you want to transform. So what it does, it shows the probability of an event happening. Either it's 0 or 1, and at 0.5 is it where it flips from 0 to 1. And this is the function that is the core of logistic regression. All right, so representing the model, logistic regression uses a equation as the representation. So it is very similar to linear regression. So the input value x is combined linearly using weights and coefficients to predict an output variable y. The key difference between linear regression and the logistic regression is that the output value being modeled is a binary value. So it's either a 0 or 1 output rather than a numerical output. All right, so here is the equation where y is the predicted output. Beta 0 is the bias or intercept term, and beta 1 is the coefficient for the single input value, x, and each column in your input data has an associated coefficient, and the actual representation of the model that you would store in memory or in file are the coefficients of the equation and the beta values. So it's going to be a very light model. And as I said, it's an eager learner. So it's going to train and find these coefficients, and that is all it stores to make the prediction. Okay, so let's talk about the log reg model. So the beta value B of the logistic regression algorithm, it must be estimated from your training data. And this is done using maximum likelihood estimation. So maximum likelihood estimation is a common learning algorithm used by a variety of machine learning algorithms, although it does make assumptions about the distribution of your data. So it's more on this we'll be talking when we are preparing the data in the notebook. The best coefficients would result in a model that would predict a value very close to 1. We are not going to go into the math of maximum likelihood. It is enough to say that a maximization algorithm is used to optimize the best value for the coefficients for your training data. Well, let's talk about making predictions with the algorithm. So logistic regression models, the probability of the default class, example, the first class, it is as simple as plugging in numbers into the logistic regression equation and calculating the result. For example, predicting whether a person is male or female based on their heights given. So when you have an input that says, okay, for a height of 150 centimeters, is it going to be male or female? Say we have learned the coefficient of beta 0 to be negative 100, beta 1 to be 0.6, and then we calculate the probability of P of, so which is like a male given the height, which is equal to 150. So we just input the values in the equation we talked about 2 slides back, and we will get the probability. And we can see the probability of the class being male is 0.0004, which suggests that it is probably a female. So this is how the predictions work for a logistic regression algorithm. Now, we want to talk about assumptions that go with logistic regressions. So the first thing, the main thing to note is that there should be only binary output variables. That is, there must be a obvious sections, like 2 values that the classification is going for. It's either 0 or 1. So male or female, success or failure, spam or not spam. So those kind of examples are the ones that you can use for our binary output variable, examples of binary output variable. And then you don't have to have outliers and other influential values. So you need to remove the noise, okay? So logistic regression assumes no error in the output variable. So you have to make sure that your data is as clean as possible. And then the third assumption is that it is a Gaussian distribution. Because it is a linear algorithm, it does assume a linear relationship between the input variables and the output variables. So you can do data transformations like taking log or root to make sure they follow a Gaussian distribution before feeding it into the model. And then the last two more points, remove correlated inputs. So this, again, like if you followed our last webinar, you should know that another biggest assumption in linear regression is that we don't correlated inputs can lead to overfitting. So the model can overfit if you have multiple highly correlated inputs. So consider calculating the pairwise correlation between 2 variables and remove the ones that are highly correlated and fail to converge. So it is possible that the expected likelihood estimation process that learns the coefficient fail to converge. This can happen if there are many highly correlated inputs. So again, removing correlated inputs can help to solve this assumption of fail to converge as well. All right, so we talked about this already. There are three types of logistic regression. sorry, we talked about binary logistic regression before. Let's just give a quick overview of multinomial and ordinal. So generally, logistic regression means binary logistic regression, but there can be two or more categories of target variables that can be present. So based on those number of categories, logistic regression can be divided into binary if there is two, multinomial. In such classification, dependent variables can have three or more possible unordered types of classification or categories, like say A, B, and C. And ordinal, these three categories that I just talked about probably has some sort of order in it. So let's say poor, good, and very good. So all these three, we know they are ordered types, and the ordinal logistic regression addresses those types of outputs or predictions. Yes, so let's dive a little deeper into the pros and cons of logistic regression here. So logistic regression is easier to implement and interpret and very efficient to train. So it makes no assumption about distribution of class in feature space. It can easily extend to multiple classes and a natural probabilistic view of class predictions. It is not only providing a measure of how appropriate a predictor is, but also the direction of association. So it can actually show you if the predictor is associated positively or negatively with your features. It is very fast at classifying unknown records, good accuracy for many simple data sets, and it performs well when the data set is linearly separatable. So you want to have the base linear assumption to have a good logistic regression. And it can interpret model coefficients as indicators of feature importance. So the bigger the coefficient is, the more important the feature is how you can interpret that. And the last one, logistic regression is less inclined to overfitting, but it can overfit in high dimensional data sets. So one may consider regularization like L1 and L2 to avoid overfitting in these scenarios. So if you remember from last week, if you have a real estate data set, there could be so many features that are available as input, but some might not be contributing towards the predictor. So in that case, you want to apply regularization similar to linear regression to avoid this overfitting scenario. Again, cons, if the number of observation is lesser than the number of features, logistic regression should not be used. And it constructs linear boundaries. So if your data is distributed in a non-linear fashion, logistic regression is not going to give a good output. The major limitation is the assumption of linearity. So yes, again, if it's not linear output that you're expecting, then you should not be using logistic regression. And it can only be used to predict discrete functions, like classification is where we will be using this. So you cannot use it for numerical outputs. Nonlinear problems can't be solved with logistic regression. As I mentioned, it has to have a linear decision surface. And logistic regression requires average or no multicollinearity between independent variables. This is, again, we talked about in the assumption. And it is tough to obtain complex relationships using logistic regression. So for that, we have more powerful and compact algorithms such as neural networks, which is what we should be using if we know that there is no linear relationship in our outputs. And in linear regression, independent and dependent variables are related linearly. As mentioned again, we want to make sure that they are related linearly and not polynomial or other types of shapes. Okay, here's a quick overview of application of logistic regression. It's used in credit scoring in medicine. If you want to classify a user to be having diabetes or not having diabetes, which is one of our examples that Angela will be going over in the notebook. Text editing, where feature, where you want to classify a text to be in different topics, and then hotel booking and gaming. All right, let's take a quick 2 minutes break here. Angela, if you could chime in for if there's any interesting questions that we could answer.
Yes, hello, everyone. We do not have any open questions. They have all been addressed.
Nice.
So I think we're good to go unless you'd like to cover anything that's been already answered.
No, not really. So if you guys have any other questions, please feel free to type it in the Q&A. But this will be covered in code towards the end of this webinar. Yeah, okay, I can continue, I guess. Thank you.
Yep, sounds good.
All righty. Let's go to discriminant analysis. So as I talked in the previous logistic regression, when you have high dimensional data, that is a lot of features, we know that the model tends to overfit and we want to do regularization like L1 and L2. So other way to handle high dimensional data is to reduce the dimensionality. And that's where we have discriminant analysis, especially linear discriminant analysis, which we'll be going over in depth here. So what is dimensionality reduction, right? So what is dimensionality, which is the number of inputs available for us in a data set. So if you could go back to the real estate data set, I think there was about 100 features available for us, but it does not mean all 100 features are going to be helpful to us. So we want to make sure that we want to reduce the dimensionality to make a simple model and make more powerful predictions versus overfitting our data and the prediction power comes down. So what is dimensionality reduction? It is the transformation of data from a high dimensional space into a low dimensional space so that the low dimensional representation retains the same meaningful properties of the original data, ideally close, not exactly the same, right? So working in high dimensional spaces, it is very undesirable for so many reasons. Right. So, for example, the raw data, that could be a lot of sparse data, which is a lot of nulls available. And then there is the curse of dimensionality. And analyzing the data is usually computationally intractable, as in it takes more time for your computer to process high dimensional data. So dimensionality reduction is a common method where it deals with large numbers of observations and large number of variables, such as signal processing, speech recognition, neuroinformatics, and bioinformatics. All these fields have data with 1,000 rows, so not 1,000 rows, 1,000 variables. So you want to make sure that you reduce your dimensions so that you have a powerful model. So the methods are commonly divided into linear and nonlinear approaches. So approaches can also be divided into feature selection and feature extraction. So dimensionality reduction can be used for noise reduction, data visualization, cluster analysis, or as an intermediate step to facilitate other analysis. So usually the dimensionality reduction is performed before you pass that output to as an input for another model. So more input features often make a predictive modeling task more challenging to model, more generally referred to as the curse of dimensionality. So here we have techniques that can be used to simplify a classification or regression data set in order for it to be performing better or having higher predictive power. Now, let's talk briefly on the curse of dimensionality. So as I said, it refers to various phenomena that arise when analyzing and organizing data with high dimensional space. So for example, we always refer, for example, if you see here, the first one, it has just the x-axis. So all your data set, let's say one feature. So you're plotting one feature along the x-axis. So this is how the plot would look like. And it's easy to observe and compute. And if we have two dimensions, so we will have the x and y axis. So our data looks like this, and it is still easy to interpret and compute because it just involves two axes. And here you have the third axis introduced, which is the x-axis. So now you have x, y, and z. And now you can see it's 3D. So the points are distributed between three axes. It's not that hard to analyze, understand, and compute, but with more dimensions being added, let's say, again, the real estate data set where there are 100 features, you don't want a 100-dimensional model, which is so hard to interpret and so high in computational cost. So that is where it's called curse of dimensionality. So what we are going to do is reduce the dimensionality by having a dimensionality reduction algorithm. So the first, the only discriminant analysis that we'll be talking here is the linear discriminant analysis. So this is one of the dimensionality reduction technique that is commonly used, especially for supervised classification problems. So it is used for modeling differences in groups, that is separating two or more classes. And it is used to project the features in high dimensional space into a low dimension space. So for example, if we have 5 features, which means 5 different axes, we can reduce it into 2 axes by using a linear discriminant analysis. Let's talk about another example here. So we have 2 classes and we need to separate them efficiently. So classes can have multiple features, and using only a single feature to classify them may result in overlapping, such as the image shown here. So we will keep on increasing the number of features to help us classify. And as we are increasing the number of features, we will also apply dimensionality reduction. So we can properly classify, but at the same time, we are free from the curse of dimensionality. All right, so here is another example. Suppose we have 2 data sets of data points belonging to 2 different classes that we need to classify. Here, as shown in the image, when the data points are plotted in the 2D plane, there is no, so you cannot draw a straight line to classify class 1 and class 2. As you can see, there is one more data point, which is class 1, identified as class 2. So in this case, LDA is used, which reduces the 2D graph to 1D graph, and it maximizes the separability between the 2 classes. So here's how that happened. Here, linear discriminant analysis uses both the X and Y axis to create a new axis here and projects data onto this new axis in a way it maximizes the separation between the 2 categories or the classes. So 2 criteria are used to create a new axis. Maximize the distance between means of the 2 classes and minimize the variation which within the class. So in the above graph, it can be seen that a new axis is generated and plotted in the 2D graph such that it maximizes the distance between the measure of the 2 classes and minimizes the variation within each class. In simple terms, this newly generated axis that separates the data points of the two classes is plotted here, where you can see that class 1 and class 2 have very distinct position in the new axis. So here are some extensions to linear discriminant analysis. So there is quadratic discriminant analysis, where each class uses its own estimate of variance or covariance when there are multiple input variables. And then there is flexible discriminant analysis, where nonlinear combinations of input is used, such as splines. And then we have regularized discriminant analysis, where it introduces regularization to estimate the variance that influence the difference variables in LDA. And when I mean regularization, it always is L1 and L2 regularization. And a few applications of linear discriminant analysis is face recognition. So it's usually used in computer vision, where face recognition is a very popular application in which each face is represented as a very large number of pixel values. LDA here is used to reduce the number of features to a more manageable number before the process of classification. So you can see here that LDA is the first step before we pass it into the classifier model. So we reduce the number of dimensions that are being passed so that it is easy for the model to classify and have high predictive power. And in medicine, LDA is usually used to classify the patient disease state as mild, moderate, or severe based on various patient parameters and the medical treatments they are going through. And in customer identification, suppose we want to identify the type of customers who are more likely to buy a particular product in a shopping mall. So by doing a simple question and answer survey, we can gather all the features of the customers and then do LDA to help us identify and select the features that can describe the characteristic of the customer that are most likely to buy the particular products together in a shopping mall. And finally, for evaluating classifications of models. So we can classify a model. Now what? Like, how do we know about its predicting power? So we use a model evaluation procedure to estimate how well a model will generalize a new incoming data set to predict. So it requires a model evaluation metric to quantify the model performance or the predictive power. So most important classification model evaluating metrics are accuracy. And we can also talk about confusion matrix and then classification thresholds and the ROC curve and AOC. So classification and null accuracy. So classification accuracy is the percentage of correct predictions. Null accuracy, on the other hand, is the accuracy that could be achieved by always predicting the most frequent class. So for example, let's say we have to classify either as male and female. So you run it through a model and you have a classification accuracy where it says out of 100, 20 are classified as male correctly, versus null accuracy, where of the 100, all of the models are classified as male, and what is the accuracy for that? So classification accuracy is the easiest classification metric to understand, but it does not tell you the underlying distribution of response values. And we can examine that by calculating the null accuracy. And it does not tell you what type of errors your classifier is making. So you have to always compare these two metrics to know what's happening in the background. The next thing you want to know when you're doing classification modeling is the confusion matrix. So confusion matrix, it's based on the number of target classes you have. So here we have a n cross n matrix where n is the number of target classes. And it's a table that describes the performance of a classification model. Angela will be going over the confusion matrix itself in practice. But here you can see that every observation in the testing set is represented in exactly one box. So it can fall under right predictions or wrong predictions. So we will talk about the format in a bit. Here it is. So let's say we have two outputs, right? Like male and female. So here we have a 2 cross 2 matrix with 4 values. So the target variable has 2 values. Either it's male or female. Let's call here that it's positive or negative. And your model is going to make predictions. So it can predict either it's positive or negative itself. And here you can see that if the target value is positive and your model predicted it as positive as well, then we know that is true positive. But in the same case, if it is a negative class, but the prediction says it's positive, then we have a false positive class, a false positive count. And then the same way we have a positive classified as negative, as false negative, and a negative classified as negative becomes a true negative. So usually when you run a model through a confusion matrix, these are the 4 values that you can calculate. And the sum of these 4 values should be equal to your test data set. So let's say if I pass in 100 data sets to make the predictions, then the sum of these 4 values should always be equal to 100. We just talked about what is true positive, what is false positive, what is false negative, and what is true negative. So you want to make sure that you were able to understand each of these values to calculate the metrics such as accuracy, F1 score, sensitivity, specificity, and false positive rate or precision. So we will talk about all of these metrics, and these metrics are calculated from just this confusion matrix. So it's important to know that you know what a true positive is, a false positive is, a false negative is, and a true negative is. All right, let's so again, this will be discussed in detail in the collab notebook. The next topic is adjusting the classification threshold. So if you remember the sigmoid function that we talked about in the logistic regression, it turns from 0 to 1 in prediction through a threshold of 0.5. That is 50% of, if the probability is less than 50%, it would classify it as 0. And if the probability is more than 50%, it would classify it as 1. And this is the default in any classification model. And this threshold can be adjusted to increase the sensitivity or specificity of the model. And they both have a very inverse relationship. So if you increase sensitivity, then specificity would decrease. And if you want more specificity, then the sensitivity would decrease. So adjusting this threshold should be one of the last steps that you would do in your model to based on your domain knowledge and the problem you're trying to solve. So before doing this, the most important steps would be building the model and selecting the best model. And once you have selected the best model, so let's say you want to predict if a user has cancer or not, and you have a classification model, right? In that case, you want the threshold to be as high as possible so that the more the probability that person would have cancer is when you want to notify that person to come in for a checkup or to take more tests. So the threshold for that should be high. So it should have high sensitivity, but it can have less specificity. So again, the whole threshold is based on the domain that you will be working in or the problem that you're trying to solve. So the other thing that you want to see is the ROC curve. So try answering the question, wouldn't it be nice if we could see how sensitivity and specificity are affected by various thresholds without actually changing the threshold, right? So let's say your sensitivity is going higher. How is it affecting our problem? It would be good to know, right? And that is where ROC curve can help to choose that threshold that balances sensitivity and specificity. So you can see here that the threshold used to generate the curve. So you want the true positive rate here to be close to 1, which says that it classified exactly what the output labels are. For example, in the cancer, let's take the male and female problem. So based on height, it classified all the males to be males and all the females to be females. In that case, the classifier is working perfectly well, and that is exactly what we want. But it is not always going to be the case, right? So it's going to be making a lot of false negatives and false positives. So your curve, it's going to be like this. So you can, and the baseline model or the random classifier is going to be the red line here. So what you want is you want to approach this point, but you cannot get that point, but you want your model to perform something similar here. So the more the curve is towards 1, the better the classifier is. So that's how you interpret this. And you can plot this for all your classifier models to see how good the performance is. And you can choose the model that has a better sensitivity and specificity. And here, as I said, you are creating a model that is reaching the perfect classifier. So as you can see, the model, as it reaches the perfect classifier, the area under the curve is increasing. So that's where we come for AUC, where it is the percentage of ROC plot underneath the curve. So you want your AUC curve, the percentage, to be as big as possible. So AUC is useful as a single number summary of the classifier's performance, which means the higher the value, the AUC curve, the area under the curve is covering a lot, and hence your model is going to be high in predictive power. So if you randomly choose one positive and one negative observation, AUC represents the likelihood that you classify will have a high predicted probability towards the positive observation. AUC is useful even when there is a high class imbalance. So you don't have to worry about imbalance in your data set. You can still have AUC and see how good your model is performing. So we talked about two things: the confusion matrix and ROC and AUC curve. And the confusion matrix is not it's the first step of evaluation. So you need to know the confusion matrix to compute your accuracy, F1 score, sensitivity, specificity, and more. And then ROC AUC curve is another thing where you don't have to worry about your classification threshold, but you can use it to see how well your model is performing. And now let's try coding and seeing how logistic regression and LDA works in a example. And this will be conducted by Angela. Angela, if you're ready, you can take over now.
Yep, sure am. Just let me
Awesome.
turn on my video here and set up my screen.
Yep.
Sneha, can you allow my video to be
Oh.
blocked right now?
Oh, yes. Okay. Give me 1 second.
Sure.
Yes, now you should be able to.
Okay. All right. Hello, everyone. Okay, so Sneha, can you confirm that my screen is showing?
Yes, we can see your screen.
Okay, great. So again, my name is Angela. I will be doing my best to walk through this great code that Rishika had prepared for us. So yeah, again, bear with me as I'll be going through this to the best of my ability, and Q&A will still be going on, I believe, during this part of the session as well. I will say, for the sake of time and just making sure that we cover everything, I will be more focused on just explaining the steps of the code itself and what everything is doing, rather than so much an explanation of why. Of course, the why I think was explained very well by Sneha, going through all of the explanations through the slides. So this is more of a how walkthrough of how can you proceed with these concepts. All right, so let's jump in. There's a nice little graphic here to show the difference between classification and clustering. Again, classification, it will predict a result based on a predefined class. So in this case, it's type of animal, and the clustering will group together the records based on a combination of similarities. It finds the patterns and groups them together with no label. So it's a fun picture there. Okay, so let's start with logistic regression, kind of going back to the beginning of the content. You'll see another nice graphic here, which does its best to try to find the line that best separates the two classes. To start, we're importing pandas. We'll be using pandas quite a lot for its data frame manipulation and capabilities. And then the data set for the diabetes data set that Sneha had mentioned is available here on Kaggle. So the first step here is defining column names that we're interested in for this example and loading the data set specific to and naming the columns according to those names. You'll see in the print of the top rows that this actually did have a row of column headers. It imported it as the first row of the data set because of this specification here of header equal to none. So a nice kind of step to clean that piece of it. We're redefining the PIMA data set as first row on to kind of remove that header row, that header record. And a reprint, and you see that that row is gone. We now have a nice clean data set to work with. Okay, so we're going to go ahead and say that for the sake of example, we already know which features we want to use for our modeling. And they are pregnant, insulin, BMI, and age. And the label in this case is the presence of diabetes. So we're going to go ahead and separate this data frame into one matrix of all of the features and a separate vector of the labels. So that's what these two steps are doing here. And then this next section of code is very important. Rishika has decided to use the scikit-learn model selection train test split functionality and package to very nicely split our data into both our training data sets of features and classes, as well as our test set features and classes. And that can be done really well in one line of code here I'd say my recommendation is to learn this package as best as you can. You will be using it a lot if you are planning on doing machine learning as part of your work. So now we have 4 different data objects here. We have xtrain, which is our training set of features. The X refers to kind of the input concept of the features. Also, it will output the test data frame of your features. Then you have the training data set labels, which are Y, and your test set labels, which we'll check our predictions against here. Okay, so again, using scikit-learn, we'll import the logistic regression. First, you have to instantiate the model object with this line of code. It's pretty standard. So now you have this instance of a logistic regression classifier as logreg here. And then all you have to do, which is really nice, is you pass in your training data set input features and then your training data set labels, so your response, into the fit function for this logistic regression classifier. So now you have a fit model in this logreg object. So to make predictions, what all you have to do is call the predict function on your logistic regression classifier. And you in this case, we're going ahead and passing in the features of our test set to get our test prediction vector as the output, which is noted here as the ypred class. So now we can use this to calculate the accuracy of our model. So again, from scikit-learn, we'll import the metrics component. And within metrics, you can use the accuracy underscore score function to quickly calculate this. You will pass in your output, your response of the actual data. So these are the actual labels, if you remember from the original train test split. And you're going to compare that with your new predicted classes. And it will calculate your accuracy for you. So in this case, accuracy is approximately 0.677. Now this number on itself is not kind of conclusive in whether this is a good model. We have to compare this against the null accuracy to understand if it's performing well. So first we need to understand, okay, what are the distribution of our classes in the original actual test set? So using value counts, we are getting a nice count grouped by the label. So we see there's 130 cases with a label of 0, which is no presence of diabetes, and then a count of 62 for the diabetes class. So we'll keep that in mind. We'll use these later. Then we're going to calculate the percentage of the ones. So to calculate this, you can simply use mean because it's zeros and ones. And if you calculate the mean of all the zeros and ones, you will get the proportion of that value. So we have that there. And then to calculate the percentage of the other class, you can simply subtract that from 1 because it's basically the opposite. And let's see here. Great, so to calculate the null accuracy, you simply take the max of the two. And then, oh, sorry, that's one step. But to calculate the final null accuracy, you're basically going to look at, okay, you're going to look at the count of values that have the negative class, which is 0 in this case. So this is looking at that value, the value counts of your test labels. The first printout of this is the count of your zeros. So it's basically the count of zeros in your test set divided by all of the records in your test set. And you'll see that, so the prevalence of the negative class is 0.677. So that's one step that's good to make. You'll see that it's very similar to your original accuracy. So what that is saying is that the model, my interpretation of this, and anyone else can feel free to respond in the chat with their own thoughts. But my thought on this is the model can simply predict 67.7% of the time, and it'd be pretty safe because that it's matching the prevalence of those records. So it's kind of just using proportions. So the model itself doesn't seem to be adding much value, but that's my interpretation of that based off of the presentation from earlier. So we might want to look deeper into this data given this outcome. So here we can look at, you can print any of the vectors of the labels, whether you're looking at your predicted labels or your actual labels. So we have some printouts of that here, just as a visual example. But more importantly, I think we want to go ahead and look at the confusion matrix. So within the metrics package, you can calculate and print out the confusion matrix by passing in your actual labels and your predicted labels. So this is what we're getting in our case, having this type of structure. So now here's another printout of comparing our actual true labels with our predicted true labels. So we can kind of look one-to-one and see, okay, this one was incorrect, these were correct, this one was incorrect. It's just something you might want to look at as general visibility. But another thing that you can do is you can calculate these different metrics that Sneha had went over. TP is true positive, so this is where your predicted and your actual are both a 1, so predicted with that positive class. True negative is it accurately predicted the lack of diabetes. False positive is it incorrectly predicted that there was diabetes, and false negative is that it incorrectly predicted that there was no diabetes. So that's kind of how you look at these counts in that order. So I think perhaps more in depth on metrics that you can compute with this confusion matrix. There's a nice walkthrough here of each one that is of importance. So this section of code here is showing the manual calculation of accuracy, where you take basically all of your correct predictions divided by all of your predictions. So this is the correct predictions of positives and negatives divided by the sum of all of the records in your test set. Alternatively, you can use the metrics function accuracy score to calculate this, and you'll see again this 67.7% coming out in both. To understand the classification error, it's simply the opposite of this. So we end up with a 32.3% approximately. And let's talk more about specificity. So specificity is more focused on how well the model is doing in preserving the lack of the diabetes label. So it's saying how often is it correct that there's no diabetes, basically. So you can do this by dividing true negatives count. So this is an accurate prediction of negatives divided by all of the actual negatives in your data set, which include where it got it wrong and where it got it right on those negatives. So our specificity is pretty good at 87.7%. False positive rate is another common metric. You look at basically how often did it incorrectly predict a positive divided by all of the actual negatives. And this is also just the opposite of specificity. So you can do 1 minus your specificity score to get this. Great. So the next code chunks are referring to a different way to visualize your confusion matrix. So Rishika has gone through some code, which I think is pretty nice, because I think you can pretty much copy and paste this and plug in your confusion matrix here to get this nice visual with our actual numbers. Okay, and in adjusting the classification threshold, keep in mind that most classifiers are going to predict if the probability of the positive class is more than 50%, it will predict that positive class. If it's less than 50%, it will predict the negative class. But you can actually adjust that threshold as was previously described. So you can use this functionality where instead of printing the predicted class, you can actually print out the probabilities that resulted from your classification model. So of the test set, these are basically the predictions of, for each record, this is the probability of a 0. This is the probability it calculated for a 1. So that's why each of these will sum to 1 together, and it's per record. In this section of code, we're basically reprinting this, but only printing the second value of each of these embedded vectors here. So these are the probabilities of your positive class, the first 10 of them. So we're going to go ahead and store the full array of all of our predicted probabilities into this object here. And then the rest of this code is some visualization code to allow you to kind of visualize the prevalence of each of those predicted probabilities in your test set. So you'll see that quite often the model it's a bit skewed. It's quite often predicting about 20 to 40% probability of a positive class. And it's probably not coincidence that that's because the prevalence of the positive class is around those ranges. So there might be some justification to lower your probability threshold, or your classification threshold, to a lower number than 50% in order for it to predict a positive class label. Okay, the next section is linear discriminant analysis. I see we are running short on time. There's a lot of great code here. I admittedly am not a super fluent in LDA. I have used some PCA in my experience, which one of the Q&A questions that I thought was really great was, what's the difference between principal component analysis and linear discriminant analysis? I'll go ahead and tell you that LDA, they're both linear transformations for dimensionality reduction, but LDA uses the labels, so it's a supervised technique. PCA is an unsupervised technique. It ignores the labels entirely. But there's a nice graphic there to kind of show you how it's trying to find the plane that will best separate the values and reduce the dimensions. Okay, so we got a new data set here. This is the iris data set, which contains 3 different species of flower. All the names that we're going to import as headers here. We have some data pre-processing. Again, we are splitting training and test using this package in the same way. And one pre-processing step that I think is really great to include here is we're going to scale all of our features. So all of the different features, which are sepal length, width, and petal length and width, they have varying scales. So often a way to enhance your model is to scale all of your features in a standard way. So we get to use the standard scalar object instance to transform our features into that new scale. Makes all the other calculations more effective. Here's an example of importing a scikit-learn component called linear discriminant analysis. It looks like we're instantiating it here. And now we're going to transform our training and test set using that instance of LDA. So it's going to look for that dimensionality reduction as part of this step. So now we're going to use our new train and test set to pass it into a random forest classifier. So similar type of pattern of steps, instantiating the classifier, and now we can fit our now processed reduced dimension training data. And this is pulling out our vector of predicted labels. And now we can evaluate. So in this case, there are three classes. There's three different species of flower, and that is our response. So the confusion matrix is no longer a 2 by 2. This is another QA element that I thought was a good question. This is a tertiary matrix where you have three labels and you have to basically plot all of the predicted against the actual label. In this case, our accuracy is perfect. This is a great example of where the pre-process steps probably helped make this possible. And here's the visual again, the nice visual of your confusion matrix where it shows you how well it's doing. Okay, so we have 3 minutes left. Sneha, do you want me to continue?
No, Angela, I think you did explain LDA properly. I think we should stop here just because we have only 3 minutes and I thought I should address some things here. So yeah, thank you. If you would stop sharing the screen, I could share a little bit. So thank you for listening to our presentation. I just want to clarify on a few things here. The biggest question that's being asked is why, can you guys see my screen? Angela, can you see my screen?
Yes.
Okay, awesome. So I just want to say that these are images and they are not replicas of the data being evaluated. So I just want to point to that there's going to be a different number here. So please ignore those. That is one of the biggest questions. And thank you, Angela, for going over LDA and logistic regression. I just thought I will start by recapping what we went through today in our presentation. So we started with what is a classification versus a regression model. We actually started with the types of machine learning. So there is unsupervised machine learning, supervised machine learning, and reinforcement learning. And classification falls in supervised machine learning model. And it is similar to regression as in it deals with linear data, but there is some difference between the classification and a regression in that classification is usually used to do categories or classes versus regression is used to get a continuous numerical output. So we saw this nice little example of predicting if tomorrow is going to be hot or cold is a classification problem versus predicting the temperature of tomorrow is a regression problem. And then we went deeper into naive Bayes classifier, the conditions that helps the classifier be strong in predictions. And then we walked over logistic regression, how it implements a logistic function to predict the probability of an outcome. So for example, in the code that was walked over by Angela, we saw if a user has diabetes or not based on the probability of the function itself. So usually there is a threshold. So we talked about that as well. So usually the threshold is 0.5. So anything above 0.5, it is usually going to the positive class of the user has diabetes versus the negative class, which is less than 0.5, then they belong to the negative class. And then we talked about discriminant analysis, which comes handy when there is a lot of features in the data set that we are evaluating, like, for example, real estate data set. So what happens here is if you're doing logistic regression for classification or any other model, there comes a curse of dimensionality where a lot of features which can be highly correlated with each other or do not have a linear functionality attached to them can reduce the predictive power of your logistic regression. So in those cases, we want to reduce the dimension so that it helps support the predictive power of your model. So what we do is we do a different type of any type of discriminant analysis to pass it over to another model. In here, we could pass it over to logistic regression. So that is discriminant analysis, where you reduce dimensionality. And as Angela very well described, there are many types of dimensionality reduction algorithms. Here we talked about LDA, and PCA is another unsupervised model where you reduce dimensionality without knowing your output or the classes. Then we talked about evaluating classification model. We saw what a confusion matrix is, how to identify a true positive, true negative, a false positive, and false negative. And then we talked about different metrics that you can calculate from the confusion matrix itself, like accuracy, sensitivity, specificity. We also talked about ROC and AUC curve. So these are important. So you can, I would suggest that when you're evaluating a model, you both look for the ROC and AUC curve and the confusion matrix. But most of the times, confusion matrix, calculating these different metrics from the confusion matrix is useful enough to evaluate your model. And then lastly, we have strategies of imbalance data, which we did not go over today. It's mostly because we had to take over this last minute and we couldn't really prepare that for you guys. But I do highly encourage to go over the content that is available here. So we have theoretical part of how to deal with imbalance data and how to do undersampling, oversampling, and how to generate data synthetically. So we have some nice slide put together by Rishika on explaining how to do all of this. I hope you found this helpful. Thank you for joining us today, this Saturday. I do have some more things to talk about before we say thank you. I want to talk about next week's session, which is on statistical machine learning. So these are machine learning models that implement statistics concepts behind scenes. So the first thing would be k nearest neighbors, and then we'll also talk about tree models, bagging, random forest, and boosting, and it will be taken by Snigdha, who will be joining us next week. I also want to talk about our panel discussion, which is going to be the series finale, which is going to be there in 3 weeks. We have an exciting panel where we are going to talk about a lot of things like career transitions, how statistics is very important, the different journeys and interesting anecdotes from our 4 speakers. Angela, who was in our session today, she's been really helpful. Thank you, Angela, again. And we also have Madhurima, who took the regression and predictions session. And then we have Laura, who will be taking the last session of this series. And we also have Vandana, who did the data visualization series. And it will be moderated by two of our very own, Sumana and Rishika. So yes, I'm excited to learn a lot from all of these four speakers or the panelists. And it's going to be a panel discussion, more of a casual discussion, just trying to learn from these four bright minds. And again, last but not the least, please join us in our Slack channel. And we have a very wide community, a global community that's ready to support you in your career. And we have so much resources, so many free resources available to you. And once again, thank you so much for being wonderful audiences. And thank you for all your feedback at the end of every session. We really take them seriously, and we try improving with each session. And yeah, that's it. That brings us to the end. Thank you so much for being wonderful audience. Thank you so much for all your support. And if there is questions that you would like us to answer, please reach out in our Slack, and we will love to answer those questions. And have a great weekend, and see you all next week.